Hi everyone, my name is Sepide. I'm going to present our recent tool Approver, which is a joint work has been done in University of Lugano in collaboration with Florida State University. We all know that software passes through a long chain of frequent changes, and most of the time, if we try to re-verify each version of the program separately over and over again, it's not going to be practical. In order to enhance the scalability, especially when it comes to an industrial size program, we can avoid the repetition in analysis of the program revisions in a sense of incremental verification, or we can also leverage the power of SMT solvers. In this talk, we are trying to combine these two techniques to gain the efficiency and the scalability by reusing the efforts of verification from one run into another. And for this, our main instrument will be function summarization technique based on Craig interpolation. And we also try to exploit SMT encodings and the corresponding SMT reasoning. To illustrate the concepts our tool uses, let's look at this simple C program, which contains multiplication, which is known to be a very expensive operation for bit blasting in SAT encoding. But instead, if we encode this program with linear real arithmetic or some lightweight theories like uninterpreted function, we can actually quickly verify such program. Let's focus on this assertion. Let's say this expensive function is abstract away with some formula like this, which exactly over approximates the behavior of the function. And let's keep this somewhere and imagine a new version comes with some changes. The question will be whether can we use this nice and compact summary instead of the new function. This will be exactly the core question in our tool. So let me introduce Approver, which is a bounded model checking tool, which we are trying to incrementally verify program revisions written in C. In algorithmic level, Approver is similar to the evolcheck, its predecessor, and actually it has several new features, which I'm going to list here. So the first would be offering a new level of SMT encoding, such as EUF and LRA. It also leverages the tree interpolation system in SMT and trying to localize and speed up the checks of new versions. Furthermore, due to the flexibility in the using of SMT encoding and abstraction using function summarization, the tool provides the trade-off between precision and performance. Finally, our tool is capable of repairing the already generated summaries to make them available for next runs. Before going to explain these new features in detail, I would like to give some quick background on the key notions of the Approver technique of function summarization, which is basically a technique to create and reuse the over approximation of the behavior of the function. So since it's expressed over the input and output parameter of the function, it tends to be so compact that it only contains the relevant information with respect to the properties. Now the question is how to end up with such summary. The idea is when we obtain a proof of unsatisfiability from the SMT solvers, we can derive summary by applying a Craig interpolation. So the definition is if we have two unsatisfiable formulas, A and B, the interpolant I will be the third formula that over approximates the fraction A, and this formula is still unsatisfiable with fraction B. And the symbols must be defined over the shared symbols of A and B. So here I would like just quickly emphasize that in order to guarantee the algorithmic correctness of the approver, we need some sort of specialized form of Craig interpolation. And to do so, we need to check tree interpolation property amongst the interpolants in the function call trees. Unfortunately, I don't have time to go into the detail of this idea. That's why I encourage you to check our upcoming paper, which is going to appear in SAS conference. Here, I would like to give a flavor of how approver works with different revisions of C program and how we really manage to verify the revisions without going to verifying the next version from scratch. So here is a main function together with some nested function calls. And if we encode this program with first order logic together with the negation of assertion, it would look like some formula like this. So basically each parts correspond to the actual representation of these functions. So we pass this formula to SMT solver, and if the results happen to be unsat, we will have a proof of unsatisfiability. Therefore, we can interpolate over different fragments of this formula. Let's say we partition the formula in two parts. The first part will be A, which corresponds to function G, and the rest of the formula will be the rest of the program. And for this, the resulting interpolant, we can get a summary corresponding to the function G that over-approximates this function. And we iterate this process for all the partitions in the program, and we store all the summaries in the external database. So imagine a new version of the program comes, and we here see that function Z has changed. Here, ideally, we would like to check if the old summaries of Z is still a valid over-approximation of the newly changed Z. Instead of verifying from scratch the second version, if we manage to check this validation, then we can conclude that the second version is also safe. So now let's proceed with this checking in a sense of incremental verification. So first we check that if summary of Z over-approximates the actual representation of the new body of Z. If the result is valid, the change has been safe, and we can conclude that the new version is also safe. Let's say this check is invalid. So what we do, we have to propagate towards the parent of this node, which is function X. So basically, we invalidate the summary of Z, and we have to check if the summary of X captures all the formulas in this subtree. And whenever a summary in the subtrees are available, we try to use that one. And if this check is valid, so we mark this function as safe. So basically the whole version will be validated and reported as safe. So in this stage, not only we manage to verify the second version, we also try to repair the already invalidated summaries and update the summary store for the next runs. Main SMT encodings that are being used in the approver, the most lightest one is equality logic with uninterpreted functions, and also linear real arithmetic, especially when the program contains some arithmetic operations. That comes quite handy. And in order to achieve the most precise reasoning, sometimes we would need propositional logic, of course. So let's put all the pieces of approver together and to see how everything works together. As an initial step, so when we have a base version of the program, we would do the bootstrapping check in order to generate the summaries and store it somewhere. We have the program and the corresponding summaries in 3 levels, in EUF, LRA, and propositional. Let's say a new version of the program arrives. What we do, first we perform a syntactic difference analyzer between 2 versions, and we mark the modified functions. And then the summary validation module trying to traverse over the functions from the bottom of the call tree towards to the root of the call tree. And each time it communicates with SMT solving, and when the summary has been validated, a new summary ideally will be generated if there are some invalidated summaries in the subtree. And then if all the changed functions have been validated, so the result will be safe and together with repaired summaries. But let's say if we traversed all the changed nodes and we reached to the main function, then in this stage we report the new version. P2 is unsafe, and also the error trace will be reported. The underlying technology behind Approver is, as a backend, Approver uses SMT solver, OpenSMT2, both for SMT checks and also SMT interpolation. This is an in-house solver, has been developed from 2010 in University of Lugano. And for the symbolic preprocessing of the C program, and also for translation into a GoTo program, Approver relies in CProver framework, but the rest of the translation into SMT encoding are the new contribution of the Approver. Since we try to encode our programs in lightweight theories and also using the function summarization, which is kind of abstraction, so therefore sometimes refinement is mandatory to check when the summary validation fails or when the formula is basically set. So what we do in both cases, so when the summary validation fails, if there are some summaries involved in the check, so basically we replace those summaries with the precise encoding of the function, which is called downward refinement. But if there are no summaries in the subtree, we basically propagate the check to the parents of the nodes, and that's called upward refinement. But when we reach to the main function of the program, therefore we have to change the theory encoding to some more precise theories if it's possible. In order to evaluate our tool, we conducted an extensive benchmarking over revisions of Linux device drivers. So you remember in the beginning of my talk, I was emphasizing that there are 2 ways to improve the scalability. So the first one was to reuse the information as much as possible between 2 verification runs. So therefore, the first set of our evaluation focuses to see the impact of summary reuse. And for this, we compared Approver with a non-incremental verification tool called HiFrog that shares the same front end. And the result was, in both theories, was quite successful, and we noticed that Approver significantly outperforms the non-incremental standalone verifications. Second set of evaluation, we were interested to see the impact of theory encoding in Approver. So for this, we conducted experiment to compare Approver against the SAT-based incremental verification tool, basically its predecessor. And here again, as you see, most of the points basically represent one verification runs located in the upper triangle that shows that theory encoding, both LRA and EUF, significantly outperform the propositional encoding. So, and the interesting result that we got here is in propositional encoding, the number of times out were more than 1300, while in LRA or EUF encoding, we only got 15 times out. That was quite impressive results. But here again, I highlight that due to the use of lightweight LRA and EUF encoding, we ended up in some situation that the result was set, the one I'm pointing in these vertical lines. So these results refer to the benchmarks that the result is set. We don't know if it's a real error or it's spurious. Therefore, we have to check with some more precise theories. But the conclusion of this set of extensive evaluation was that LRA and EUF in total performed quite nicely. As you see, this is like less than 5% compared to the number of initial benchmarks we had. And that's quite nice to achieve the scalability. But of course, there are some situations that we would need precise propositional encoding. We were also interested to see the difference of LRA encoding and EUF encoding performance-wise. And we noticed that in general, LRA has an almost 30% time overhead compared to EUF encoding. And we guess this overhead might be because of the expensive simplex algorithm that LRA conducts. We also compared Approver with CPA checker that has incrementality using precision reuse in the predicate abstraction. And there also Approver got quite nice speed up compared to CPA checker. But here I must add some disclaimer that this sort of experimentation might not be precise because the tools are quite different, because Approver is a bounded model checking while CPR checker is unbounded and working with loop invariants. The related work, so EvolCheck as a predecessor of the Approver, and there are also some nice incremental verifier in the community, but they are all different than Approver. As a future work, we would like to extend Approver to handle mixed theories. Basically, we would like to have summaries such that to work across different theories. For this, the challenge would be to making sure that the tree interpolation property are preserved. And one way would be checking that on the fly. As a conclusion, I introduced Approver, which is an BMC tool for incremental verification of C program versions. And it only focuses on the modified code, and therefore it's a cheap local check. And the new features of the Approver, I would say that it offers different SMT encodings, such as EUF, LRA, and propositional, of course. And it leverages the power of SMT level summarization algorithm. And since, because of these two layer of encodings and the summarization, it gives a good flexibility to adjust the precision and efficiency of the verification. And most importantly, Approver is capable of repairing the already generated summaries on the fly to make it available for the next verification runs. Therefore, putting all these techniques together, it's been shown that it's quite scalable when it comes to verifying the large program versions. I would like in the end encourage you to check our website and also to check out our tool, which is open source, and I will appreciate any comments. Thank you.